Hello guys and welcome to my YouTube channel. So today I'm going to be solving a very recent paper, October-November 2024, question paper 1-1 for physics. So we're going to start off with the first question. What are the SI base units for the moment of a force? So you want to understand what a moment of a force actually is. So a moment is basically the turning effect of a force. Imagine you have a lever and you're trying to push it up and down. There's going to be a turning effect, right? So that's what we call the moment of a force. So the formula basically for the moment of a force is actually the force itself multiplied by the displacement. But I know force is mass times acceleration. So here I'm going to have mass multiplied by acceleration multiplied by my distance d. So my mass is kg, my acceleration meters per second squared, and then d is just m. Those two multiply together. I get kg m squared s to the power of -2. Then I scavenge through my answers and the correct answer will be D. Hope that makes sense. Okay. Which statement about vector quantities is correct? If I look at my answers, acceleration is a vector because it has a constant magnitude. Well, you're not only a vector because of constant magnitude, but also because of direction, right? Temperature is a vector because it can be positive or negative. Well, we don't really talk of direction for temperature really. And time is not a vector, it's actually a scalar. Weight is a vector because it has direction. That's actually true because weight can either be up. For example, it can be, let's say, negative if the acceleration due to gravity is forcing you to move down, right? So we can be able to say, oh, weight is a vector because it has magnitude and direction. Okay, hope that makes sense. The next question, the density of the material of a rectangular block. So I'm going to give you a rectangular block on the side, guys. Hope you can see it. Okay, so it has dimensions, length, width, height. So my goal is basically to calculate the uncertainty in the result. So whenever you have an uncertainty problem, I want you to go through this framework that always works for these kind of questions, right? So number one, always ask yourself, what is the formula in question? And be as clear and simple as possible. Okay, so if I'm thinking about this kind of question, the formula basically is density is equal to mass over volume. You can take that a step further and say density is equals to mass over length times width times height. Okay, and the second part of all of this is to have your uncertainty equation, right? Or I like to call it my UF, my uncertainty equation. Okay, so how that works is that you look at the quantities on the left-hand side and the quantities on the right-hand side. So in this kind of scenario, it's essentially just going to be delta rho divided by rho is equal to, then you look for all the quantities on the right-hand side. If they're constants, don't include them. Just look at the quantities themselves. So that's going to be, okay? Then after that, pure substitution in order for you to then calculate the answer. So in this particular question, delta rho would just be equivalent to, take all your quantities and just put them all together. Then you take all of that and you multiply by your density. So times 2.50. Punch that in your calculator and you get 0.05. The uncertainty and the answer will be C. You're in a Cambridge exam and you've been asked what is a reasonable estimate of the volume of one page from your examination paper. How are you going to tackle this? The trick with reasonable estimates is to get as real as you possibly can. So what you're going to do is you're going to grab your examination paper, take a ruler, you're going to measure the length of that examination paper. Okay, you got it? So roughly I'm getting here, because I'm also doing the calculation with you guys, I got about 30 centimeters, right? So 30 centimeters. Remember, it's a rectangle, guys. Length times width times height. Okay. And then you're going to measure the width of that paper, right? So you have the length. You want to measure the width. So here I'm getting about 21 centimeters. 21 centimeters. Okay. So convert that to millimeters. So you're going to have 300 millimeters times 210 millimeters times. The height is going to be the problem. How thick is an examination paper? You can't do that practically, guys. So what you're going to do is you're going to get that paper and you're going to measure the thickness of, let's say, 10 pages. And for me, my realization, I realized, oh, all of those 10 little sheets are actually equivalent to about a millimeter, right? So that means one sheet would just be 1/10 of a millimeter. In other words, that would be 0.1 millimeters. Okay, Just a little calculation. Measure for 10 sheets, then divide 1 by 10, and you get 1 over 10. Okay. Then if you multiply all of these quantities together, 300 by 210 by 0.1, you get about 6,300 millimeters squared. Right? And you're going to look for an answer which is closer to that, and that's going to be C. So you don't have to get the exact answer that I got. You just have to get something similar to that. Okay. Number 5. An object is projected from a horizontal ground. So does not. The horizontal component of the object's velocity is constant. That's true. And there's a value of u cos theta. That's also true, because you can resolve it in 2 directions. One is this, and then the other is this. So if you want to resolve, because you run away from the angle, right? You run away from your sins, you arrive at u sine theta, right? And because you close the angle, close starts with a C, so you also arrive at u cos theta. Just an easy way to resolve without thinking too much. So the horizontal component is constant and there's a value of u cos theta. That's correct. The horizontal distance traveled, I know that S is equal to ut. So take u cos theta times t. That makes that correct. I know that the time taken for it to reach the ground is t over 2. Is t, sorry. That implies to reach maximum height is going to be half of that. T over 2 is correct. Because you kick a ball, it's going to go up and down. So if the whole time is t, the time for half of that is going to be t over 2. The vertical component of the object's velocity is constant. It can't be constant because remember, we have weight. We have the weight of the ball. So acceleration due to gravity pulls the thing down, and that affects the magnitude of the vertical velocity. So it can't be constant. It is u sine theta true, but it can't be constant. So it does not describe, and the correct answer would be D. Question 6. A person travels on a motorway, a total distance of 200 kilometers, travels the first 90 kilometers at an average speed of 80 kilometers, which average speed must be obtained for the rest of the journey if the person is to reach the destination in a total time of 2 hours, 0 minutes. So we have a car, right? Person has a car and they want to travel a total distance of 200 meters. Divide that into 2. One is 90 kilometers. That means the remainder itself will be 110 kilometers, as you can see from the diagram above. So we have 2 things happening here, and your goal basically is to find the average speed that must be obtained for the rest of the journey if you want to reach the destination in that total time. So if I were to put everything here, I have 2 things going on here. I have for the first part where I have 90 kilometers over here, and for the second part where I have 110 kilometers. I know that if I want to get the time for this one, it's going to be the distance divided by the speed, right? I know the distance is 90, the speed is 80. That's going to give me 1.125 hours. 1.125 over 100 times 60. That's basically going to be 1 hour, 7.5 minutes. Okay, so this is the amount of time taken to travel 90 kilometers. But if you were to go on the other side and you want to find the time taken for this particular thing, you know that, if the whole journey takes 2 hours, basically, if it's 2 hours for the whole journey, to travel this is just going to be 2 hours minus 1 hour, 7.5 minutes, and you're going to get the time for 110 kilometers to be 52.5 minutes. Okay, does that make sense? Okay, so if you want to get the speed, the average speed really is going to be the total distance that has been traveled, okay, divided by the total time that has been taken. So the total distance is 110, the total time 52.5 divided by 60, converting that to hours, we roughly get 125.714 approximately. That's 126 kilometers per hour. And my answer is going to be D. Okay, hope that makes sense. A car of mass 1,200 kilograms. That's a very, very light car. So I'm going to give you a little light car over there, right? Has a momentum of 18,000 kilograms per meter per second. What is the kinetic energy of that car? So that car has that mass and it's moving with that particular momentum. Momentum is just the product of mass and velocity. So what I know is that my kinetic energy essentially is just 1/2 mv squared, right? But I know that momentum is actually mass times velocity. So if I want to find the kinetic energy, I can just substitute v with momentum. So v will be momentum divided by mass. So now I know, okay, v is that, kinetic energy is that. How can I be able to find the kinetic energy? So the kinetic energy will just be equal to 1/2 times m times rho over m squared. The rest is just substitution. So I have 1/2 times 1,200 times 18,000 divided by 1,200, all of that squared. Okay, then after that, the whole computation here will give me 135,000 joules, and that would be my answer. My answer will be 1,135 kilojoules. Hope that makes sense. Okay. A ladder is positioned on icy, frictionless ground. So you have a ladder over here, right? At the instant of release, it begins to slide. So it's going to slide. So your ladder is like that, and you're going to have a sliding ladder. And we basically want to understand the direction of the forces P, W, and R acting on the ladder as it slides. So before we even do this, we want to understand what exactly is going on. So let's look at the ground. So this ground is frictionless, right? And that's important because as the ladder moves, there isn't going to be a force, a frictional force rather, because remember, the force of friction opposes the motion of that particular thing. So if it's to slide, we're going to realize that our ladder is going to move here, right? So ideally, I was supposed to have frictional force in this direction, but I don't, right? So the ladder itself is going to press on the ground, right? It's going to push the ground itself. So the ground was supposed to collapse, but the ground doesn't because it exerts an upward force like this, which is R. So I know that R acts upwards in all of these diagrams, right? So I already know C and D are wrong because the ground is being pressed by the ladder. So it reacts by pressing an upward force. Okay. But the wall itself is rough. If I were to allow my ladder to fall, if the ladder slides and slides and slides and down, it slides down, guys. So I should expect the force of friction, the frictional force, which opposes the motion of an object, to act upwards. That is what I should expect, right? Okay. And then the ladder presses the wall, right? The ladder presses the wall. So I expect the wall to press back, right? So you punch the wall, it punches you back. That's why you feel the pain. And it punches you directly, perpendicular. So I expect the wall to react in this particular manner, right? Okay, so I have two forces, one up, the force of friction, number one, the other two, the reaction force from hitting the wall hits back. So these two forces will interact and their resultant, you have a force up, a force to that side, so you basically expect a resultant force that basically looks something like that. So expect a resultant force like that, and that force is going to be P. So you can definitely see that, oh, B has to be the correct answer. R up, way down, and P at that angle. Because there are two forces. If you didn't get this and you got A, it's possibly because you ignored the force of friction. You didn't include that, so that possibly affected your answer. Hope that makes sense as to why the answer is B. Okay, question 9. We have a toy parachute. So I give you a parachute, I give you a bridge, then that parachute drops from that bridge and it falls and it falls and it falls. So we want to understand the region where we reach terminal velocity. So terminal velocity is just a constant velocity. So it's a distance time graph, and a constant velocity is experienced where we have a constant gradient. Okay, because velocity is the gradient of a distance time graph. So if I look at this graph, do I have a constant gradient at A? No, I don't. Do I have a constant gradient at B? No, I don't. Do I have a constant gradient at C? No, I don't. Do I have a constant gradient at D? No, I don't. I only have a constant gradient at B. So B becomes the correct answer. Hope that makes sense. Question 10. I give you a lift, right? An elevator that consists of a passenger car. So we have a passenger car over here, supported by a cable that runs over a light frictionless pulley to a counterbalance. The counterbalance falls as the passenger car rises. We're given some masses here. Very nice. Thank you, Cambridge. What is the magnitude of the acceleration of the car when carrying just one passenger and when the pulley is free to rotate? Okay, let's think about this. So I have a passenger car. Okay. So I expect the forces to be acting down. Okay, something that I just, anticipate should happen. Okay, so I expect my forces like this. So that's mg, right? Mg for both the person and the car itself. Okay, so this person is pulling down, but this lift has to move up. So I expect a force upwards here. Some could say tension, if you're trying to be fancy, or which I would really advise you try to be fancy, right? So if I have the counterbalance on this side, I'm also going to have weight. Okay, so I'm going to have weight acting downwards as well on this side. So I also expect to have tension also upwards. Okay, so I have two sides, the left-hand side and the right-hand side. So I can create equations because I know the counterbalance falls down and I know that the other thing falls up. So I can create two equations on one side. So I'm going to have for counterbalance, right? So I'll start for, I'll just say CB. I know that the weight is acting downwards. So I expect the weight to be acting down minus the tension moving up. All of this is what I call the resultant force. And I expect that to be equal to MA, right? Mass times acceleration. Okay, so the weight is basically 640 times 9.81. Subtract the tension. You don't know what the tension actually is. That must be equal to 640A. So that's my first equation for the counterbalance on one side. Okay. Then for the other side, it's for the car with the person included. Okay. The tension is greater for this side. So I have tension minus the combined weight is 520 plus 80. That's 600. So I have 600 times 9.81. And that's going to be equal to 600A. That's going to be equal to 600A. And I call that equation 2. So I have two equations, one equation there, one equation there. And what I can do is I can solve these equations simultaneously and get one specific equation. So if I were to simplify all of this, I get 6,278.4 minus t is equals to 648. So you can see that I can make t the subject of formula here. And once I place t here, I can then solve for the acceleration. So step by step, divide it into two, then solve both sides so that you can be able to get one specific answer. So my tension is just going to be equal to 6278.4 subtract 648. So now I have the value of the tension. I just place it there. So now I have 6278.4 minus 640. 600 times 9.81. That's minus 5886. So this is 640A. This should be equal to 600A. Okay, so if I want to find the value of A, it's basically going to be equal to this 2 subtract. They give you 392.4. You divide by 600 plus 640. You get an acceleration of 0.32 meters per second squared. So I have 0.32 meters per second squared. Okay. Question 11. I give you a bet, right? You're trying to play cricket. I've never played cricket, but I think it's a very, very fascinating sport. And the whole goal basically is you hit a ball, you run and you run whilst the ball is in the air, right? So your runs get counted or something like that. So you have a stationary ball. You're going to hit it with the bat, and the ball is going to leave the bat with velocity v. So it's in contact with the bat for a short period of time, delta t, and you want to find the average force of the bat on the ball. According to Sir Isaac Newton, the famous Sir Isaac Newton, a force is basically the rate of change of momentum. So the change in momentum divided by time. That is basically what a force actually is. So what is the change in momentum? Well, it's basically final momentum minus initial momentum, right? That's my change. So the final momentum is going to be mv because it has a mass m. It leaves the bat with a velocity v. So I should expect the initial being 0 my change to overally be mv. So my force would just be my change mv divided by the time delta t, and the correct answer will be B. Question 12. A disk of mass m is moving across a horizontal frictionless surface. So we have a little disk here, just moving on and on, minding its own business. Boom! It collides with another stationary disk of mass 4m, and they move at angles to each other. And want to find the initial velocity u of the disk of mass m. So if you haven't seen equations where momentum is at an angle, well, you've seen it now, right? So the whole point of this is that before collision, you have a certain system, right? You have a certain system, a certain interaction occurring between two different particles. Then after collision, you also have another system. And then what's happening is that they're going to diverge. They're going to move in different or in opposite directions, right? So if you have two systems, one system here and one system here. So you're also going to have what we call horizontal and vertical conservation of momentum. Remember, momentum is a vector, guys. So it's conserved in both directions. Okay. So first on this side, I'm going to have my horizontal. Okay. Conservation in horizontal. And separately on this side, I'm going to have my vertical. Then I'm going to solve my problem like that in both ways. So if I look at my horizontal, I can resolve 4 meters per second into two components like this, right? So you have 4, then you can also resolve it like this. Okay. So if you close the angle, close starts with a C, so you arrive at cos, you have 4 cos 45. But you also do that for this one. You close the angle, you have V cos 45. Okay, so those are your two horizontal velocities. You run away from the angle, you arrive at sine, right? So you have V sine 45, an easy trick to just resolve angles faster. And here you have 4 sine 45. Now you want to conserve momentum in the horizontal, and you also want to conserve momentum in the vertical, which is basically the whole point of all of this, because after doing that, we can therefore be able to have one specific thing that we can rely on. Okay, so if I want to conserve momentum in the horizontal, I'm just saying momentum before should be equal to momentum after my collision. Okay, so before collision, I had a mass m and a velocity u. So combine that, you have mu. Did you know the velocity of 4m? It's 0. So the total momentum will be 0. After collision, I had the same mass m, but the velocity was 4 cos 45 and moving in the positive direction. So in this forward direction. So after collision, I'm going to have 4 m cos 45 plus. For this one, I have 4m, but v cos 45. So I have 4m v cos 45. So they all cancel out. They all cancel out. The m cancels out. The m cancel out. The m cancel out. So I'll be left with u being equal to 4 cos 45 plus 4v cos 45. So this would have been solved if I just knew the value of v. Right? If I just knew the value of v, I could have gotten this, but I don't know that, right? So I go on to the vertical and I'm like, what if I were to resolve the vertical? Would that give me a clue as to how I can solve this question? Then I go on the vertical and I'm like, before collision, it was 0. Okay, so before I had 0, and that's very, very important because I can just say momentum before, again, should be equal to momentum after collision. So before 0, after my collision, then I look and I say, I had m, so it's m4 sine 45. m4 sine 45. But then I look at the other one, it's pointing down. So I'm going to put a negative there. So I'm going to have negative 4m v sine 45. 4m v sine 45. My goal is just to find the value of v, basically. So I have 4m v sine 45 is equal to 4m sine 45. Ah, voila. Those two things cancel out, so V will just be 1. Okay, so if I go here, I'm like, V is 1, but U is something else. Oh, so U will be equal to 4 cos 45 plus 4 cos 45 as well. So the value of U would just be 5.7 meters per second. And the correct answer for that will be D. Okay. Question 13. Hope that makes sense, right? I hope I'm not too fast. Question 13. We have planet Earth and we have the moon, right? So we want to drop an object from Earth at a height of 2 meters. So you have a height of 2 meters, you're holding an object and you want to release it. And you have the moon and you want to drop it from twice that height. So if it's 2 meters, so I'm just going to put a little illustration down here. So if it's 2 meters on Earth, it's going to be 4 meters on the moon, right? So if I have Earth here, I expect there to be 2 meters here. Then I have my object over here. But if I'm now on the moon, if I go on the moon, I'm now expecting to drop it at 4 meters. Like this. Okay, hope that makes sense. Cool. So I want to find the ratio of the speed of the object just before it hits the surface of the Earth. And you think, I'm given displacement, I'm given initial speed, and I want to find final speed. What equation can I use? You think, you'll say, I can use V squared is equal to U squared plus 2AS, right? Because U is 0. So V will just be the square root of 2AS. That's it, right? So in order to find this ratio, basically I have to say the square root of 2, the acceleration on Earth, times the displacement that it has moved on Earth, over the square root of 2 times the acceleration on the moon, times the displacement that it has moved on the moon. So if I look at this, 2 times the acceleration on the Earth, for simplicity's sake, let's just say it's 10, just to be simple, right? The displacement will be 2 divided by the square root of 2 times 16% of 10 is just 1.6, right? Okay, so 1.6 times 4. You take that, that's the square root of 40, divided by the square root of 2 by 4 is 8. 8 by 1.6, that's 12.8. Basically, you take that, you square everything, then you get 1.8, right? Okay, so I hope that makes sense, right? So the correct answer will be A. Question 14. The graph shows how the velocity v varies with time t for a bungee jumper. So you have a person going bungee jumping, then they jump off of that. So if the jumper is at rest, we want to identify those points on this graph. So you're only at rest when the velocity is 0, and the velocity is only 0 at point R. Right? This is the only point where the velocity is 0. So I know that it's R and R. Then we have 0 acceleration. Remember, acceleration is basically the gradient of a velocity time graph. So where is the gradient 0? At P is the gradient 0? No. At Q is the gradient 0? Yes, because it's a straight line like this. So it's only at Q I have 0 acceleration because that's where the gradient is 0. So the correct answer will be C. We're looking for a place or for a point where the gradient is 0, then a point where the velocity itself is 0. A solid sphere, which is less dense than water, is held completely immersed in water a few meters below the surface. So with water, you take an object, you place it in water like that. So at the end of the day, you basically have something like this, right? Something like that. So that's water. Then you have your object like so, and you place it, you immerse it in water. Okay, so if I'm looking at the forces acting on this object, I expect mass, which is mg, acting down, and I expect upthrust, which is equal to the density times g times v, rho gv, right? So I expect that upthrust to be acting up, density of water, and g times v. Okay, and then the weight acting down. As it starts to move, so the resultant force F will just be equal to the upthrust minus the weight. But the problem is, as it starts to move, it starts to build up a frictional force. But the frictional force in water is called the viscous force. So the viscous force opposes the motion of the whole system. So I expect my viscous force to be acting downwards here, my viscous drag force. Okay, so here I'm going to subtract my drag force. So the drag force increases with increase in speed. So it's moving up and up and up and up and up, and the drag force begins to build and build. So looking at this equation, if D increases, U minus weight minus D, I expect the resultant force to be decreasing. But the upthrust doesn't change. It's still completely immersed in water. What's only increasing is D, which is the drag force. So the correct answer will be A. Question 16. A uniform bar of weight 200 newtons. So you go at the midpoint here and you assign the weight 200 newtons and length 4 meters. Is freely hinged on the wall at one end. The bar is horizontal and is held in equilibrium by a cable. At that distance from the other end, the cable is at 35 degrees. What is the tension in the cable? You're looking at this question, you're like, I don't know where to start. I don't know how to solve it. Or what you can do is you're looking at that tension, right? You're like, I can resolve and basically compare components, right? I can do that. Okay, then you're like, if I were to resolve this tension and look at it in this vertical direction here, right? So you're just thinking, what can I try to do to solve this problem? This will actually be T sine 35, right? You've resolved the tension to be T sine 35. Okay. Then you're like, I can use moments because I have a pivot, I have a hinge, which is over here. So if I have this, I should expect all clockwise moments to give me values that are equal to the anti-clockwise moments. Okay, they're like, that makes sense. So I had that thought process because I'm looking at a tension and I resolved it. Then I'm like, I can't just say this is equals to this. There could be other forces acting here that I also have to resolve and equate. So I can't do that, but I can use moments. So it's either you're using moments or you're using resolving forces when you're asked to solve for these funny things. So I go in and I say, clockwise moments, the sum of them should be equal to the sum of the anti-clockwise moments. Then I go in and I say, so if I have 200 times 2 for that anti-clockwise moment, if I have 200 times 2, this one would be T sine 35 multiplied by the distance itself is going to be 3.5. So my tension is basically going to be equal to 200 times 2 divided by 3.5 times sine 35. So I'm going to have a tension that's going to be equivalent to 199.251. Roughly, that's 200 newtons. So the correct answer is going to be C. Hope that makes sense. Question 17. The diagram shows a pair of equal forces acting on a meter rule, which diagram shows the forces that provide a couple. So in zero resultant force, so a couple, basically a pair, forces equal in magnitude, opposite in direction, and are separated by distance r. So in this case, it's going to be B, because you have two forces, opposite in direction, equal in magnitude, because they're arrows of the equal magnitudes, lengths, and they're separated by some separation r. So they are a couple. And is there zero resultant force? Yes, because the force up is directly equal to the force down. So you can't have a resultant force. 18. A ball of mass m is thrown up to height h in air. You take a ball, you throw it up, as shown. A resistance is negligible. Acceleration of free fall is g. What is the total work done by the gravitational force on the ball during its flight? So they underlined total. Why would they underline total work done? What is work done? Right? You ask yourself a simple question. Well, what is work done? Is it you going to the gym, getting your biceps worked up and lifting those dumbbells? Well, that's not really what work done actually is in physics. Work done is actually the displacement times the force. Okay, so the displacement in the direction of the force times the force itself. Okay, So if you ask yourself, if I start at P and if I end at Q, what is my total displacement? You're like, huh, okay, so it's 0, right? I rose up and I fell down. So overall, I traveled up and I traveled down. I haven't really displaced much, right? My displacement is 0. I've moved the displacement in the horizontal, but the gravitational force doesn't act in the horizontal. It acts up and down. So that's the force itself, right? So the direction in that force, there hasn't been a displacement because I started at P and I ended on the ground. So because the displacement is 0, even though there's a force, the mere fact that the displacement is 0 implies that the total work done itself will also be 0. Hope that makes sense. Question 19. A spring of spring constant 30 newtons per meter is suspended vertically from its top. So you have that system over there, that's on the side, and the spring obeys Hooke's law. Nice. Initially, the spring is not compressed and not stretched as well, but a mass of 0.50 kgs is attached to the bottom of the spring. The mass is released from rest and falls. Frictional forces are negligible. What is the maximum extension of the spring? Okay, so the spring is going to move down and it's going to arrive at that position as shown. So that's the maximum possible position in which it can be stretched. Then you ask yourself, what is the maximum extension? How can I find this? Right, your brain is thinking and is thinking, and you're like, F is equals to kx? That can't work because, well, if I know k, but I don't know the maximum force possible, right? Remember, you can't just say it's equal. If F is equals to kx, then I'm at equilibrium. There isn't an extension because at the bottom, I expect the restoring force to actually be greater. Then I'm like, okay. This thing moved down, right? So the maximum possible displacement, as it moved down, it lost gravitational potential energy because I'm thinking of that downward motion. Then I'm like, but what did it gain? It gained elastic potential energy. Then like, good. Okay, so loss in GPE will be equal to gain in elastic potential energy, right? This is me just brainstorming and thinking and, all that stuff. So loss in GPE will just be mg delta h, right? Okay. Gain in GPE, we know that the formula for EPE is half kx squared. So because x is the extension, I can be like, okay, now I know what the extension is. Well, let's just make it the formula, then subject of the formula. So I know that delta h is the extension, the change in height at point A to point B. That change in height is also the same as the extension in the spring itself. So I should have 2 mg delta h divided by k delta h as well, because x and delta h are just the same. So these cancel out. So my value of x would just be equal to 2 times 9.81 times 0.50 divided by k, which is 30. Then you get a maximum extension of 0.33 meters. Right? So if you didn't get it at first go, you're supposed to think and say, what formula can I use? And it's not that clear, guys. It's really not that clear. But you're supposed to think of, I have a change in height. So what formula can I use that can help me find x? Right? And in this case, it was using the energy method. So you should know the viable possible routes for you to think. It's either the energy method or either the force methods. If you are in other concepts about equilibrium, it's either the moment method or the resultant force method, right? So you should have all those two sets so that you can solve these kind of problems as they appear. Question 20. A wire has original length L, area A, and a force F is applied, causing it to have an extension X. The wire obeys Hooke's law, which is the expression for Young modulus of the material from which the wire is made. Beautiful. So I know that Young modulus is actually equal to stress over strain. You cause a certain stress on a material, it strains. And stress is basically the force divided by area. Strain is extension divided by length. So If I look at the first one, if I leave stress in there, if I just leave stress as is, it will be stress times L over X, not stress times X over L. If I look at B, if I leave strain as is, so I will have F over A divided by strain, right? So basically it will be F over A times strain. So the correct answer becomes B. Right? You don't need to look for C and D. You've got the correct answer. But just by rearranging this equation, having strain in the denominator, we've just obtained the equation itself for Young modulus in terms of strain. Question 21. A wire is stretched gradually by an increasing force. The force extension graph is shown. Which statement must be correct? Okay, point Q is the elastic limit. That is correct. Okay, because at Q, after that, it's no longer elastic. It doesn't return back to its original length after the deformation has occurred, because this is a region that I call a region of plastic deformation, right? So I really can't have elasticity being present from Q to S, right? But then I should still understand why B, C, and D are wrong, right? For interest's sake. So point R is the limit of proportionality. No, because proportionality ends at Q as well. So that's why B is wrong. For C, the area represents the elastic potential energy stored in the wire. Well, yeah, but elastic potential energy is only stored when the deformation is elastic. Beyond Q, we have plastic deformation, and that energy is not stored, it's rather lost due to permanent deformation from this area to this area. I can't say that energy is stored as elastic potential. It's energy that is also being utilized for plastic deformation. So C would be wrong. Even D, from Q to S, I'm not stretching the wire, I'm now damaging the wire. So I can't say it's the work done in stretching the wire, it's now the work done in damaging the wire as well, right? So these are two different areas. A and B are two different areas. They don't mean the same thing. That's why D will also be wrong as well. Question 22. A spring has an unstretched length of 0.3 meters. So you do it like this, and you put your spring like this without being stretched. It is a length of 0.30 meters. And a spring constant K of 400 Newton per meter. An object is suspended from the spring, and the spring is deformed, but within its elastic limit, or within the limit of proportionality. So I'm to now suspend something here, then it deforms, but then what happens is that the new length itself will be 0.50 meters. So like what I said, elastic potential energy, if you look in your textbook, as the formula half kx squared. So if I want to find the extension x, it's basically just the difference between these two values, right? The difference between these two values, which is 0.20. So if I want to find elastic potential energy, it's just basically, well, half times 400 times 0.20 squared. That's going to give me an answer of 8.0 joules. The correct answer will be A. Move on to question 23. A wire consists of 3 meters length. And then it also consists of metal X joined to 1 meter length of metal Y. The cross-sectional area is uniform, and the load causes X to extend by that and Y to extend by that. Okay, so let's start from the first scenario. So we're going to say, for first scenario, let's understand the first scenario first, right? Okay, so for first scenario, I basically know that the Young modulus, right, is equal to stress over strain. So I know that I'm only given strain information here. I'm given the extension and I'm given the length, right? So I know that I'm just given that information. So the Young modulus, I can represent it by E. I know that stress times X, strain times L over X, because strain is X over L, that flips with L over X. So this is the equation that I'm going to be using for the whole question. And how did I think of this? I was like, The only thing that's constant in both scenarios is E. So if I can find a way to find X for both scenarios and then just add them together, because when you have things in series like this, you expect the whole system to extend together. That should be helpful. So for X, first X1, right, its E will be equal to stress times 3 divided by the extension of 1.5. Then for X2, so for Y1, I'm going to have stress again. So for Y1, I'm going to have E being equal to stress times 1 divided by 1. Okay. So E will just be equal to stress. Right? That's for first scenario. Then for the second scenario, right? For the second scenario, that's now X2. We do the same process. E will be equal to stress times, but for X2, the length for X is now 1, right? But the extension, I don't know. Then for Y2, the length is now 3, so E is now equal to stress times 3 divided by X, let's say Y, sorry. The extension, I don't know. But I know the value of E. For X, I know the value of E. E is stress times 3 over 1.5. So I can go here and I say stress times 3 over 1.5 is equal to stress times 1 over X. Multiply that, 3X will be equal to 1.5. So X will be equal to 0.5 millimeters. That's the extension for X, right? And if I want to find the extension for Y, I know that Y2 is basically stress, right? So E is just stress. So stress, right, will just be equal to stress times 3 divided by Y. So my Y will just be equal to 3 millimeters. So I know that X extends by 0.5. I know that Y extends by 3. Punch both of them together. The total extension, right? So the extension total will just be equal to X plus Y. 3 plus 0.5, 3.5 millimeters. So my overall extension, the total extension rather, will be 3.5 millimeters. I know it's a little bit complicated. How did I even think of this? Or how can you think of it yourself? Well, you're supposed to look at the length and look at the extension and try to figure out what equation can I use. I'm given area, length, extension. I was taught about Young modulus. And the force is the same in both instances. So the stress doesn't change. But I know I'm just varying L and X. Right? And I know for the same scenario, E is the same. So can I compare both scenarios and find a way to combine both of them and get the total extension? And because of that, with time, you can then be able to make that connection and arrive at the answer that we obtain. Hope it makes sense. If it isn't clear, again, guys, just put it in the comment section and I'll be able to address that. Question 24. The graph shows the variation of the displacement with distance for a progressive wave at one instant in time. What is a progressive wave? A wave just propagates energy from point A up until point B. So I'm given displacement, again it's distance, and I'm given that the period itself is 91 meters per second. What can be deduced about the wave? Frequency. I know that frequency is equal to 1 over t. And 1 over 91 times 10 to the power of negative 3. That's close to 11. Both is 10.9 something. So yeah, that's close to 11. And then the velocity is that. V is equals to F lambda. So if I have the frequency, that's 11 times the wavelength. Look at there. That's 4. So I have 4.0 divided by 100. My V is going to be 0.44 meters per second. So the correct answer is A. Okay. Is B correct? The wavelength, the velocity can't be 0.55. I just calculated it and I obtained 0.44. So B has to be wrong. Is the answer C? The frequency is correct. Yes. Is it longitudinal? I don't know. honestly. Is it transverse? I don't know. Okay. So I know some of you might have said it's transverse and there's wavelength 4 centimeters. And you're wondering, well, why isn't it wrong? Why isn't it correct? So you're told that it's a displacement against distance graph. But they weren't too specific about what kind of displacement are they talking about, right? If it's a displacement of an individual particle, that particle is moving up and down, whilst the distance of the wave itself is moving forward, I can say for sure that's a transverse wave. But sound waves can also be represented by sine waves, right? The safest thing is not to assume the wave type unless told otherwise. Because I have a question for you. What if the wave isn't showing the motion of particle? What else can it show? Well, maybe displacement along the wave direction itself, displacement of the air particles. They move back, they move forward. They move back, they move forward. That's a sinusoidal graph. That can be represented in a sine wave, showing that the displacement is back and forth, and I can represent that in a sine wave, right? So I don't necessarily have to have like, a graph representing individual particles for it to be transwave or transverse, right? It can be anything at all, right? It can also be sound waves that were present. So I can't tell if it's transverse and I can't tell if it's longitudinal. But if you still don't get it, let's have an argument in the comment section about this one, right? But just the safest thing in physics is not to make an assumption unless the question has allowed you to do so. Question 25. Which group of electromagnetic waves is arranged in order from shortest wavelength to longest wavelength? Okay, I have a little acronym here. Rick Martin is very ugly except Grace. So if you know someone that starts with an R, then an M, you can just say RM is very ugly except that person. So it's just a little funny way of just memorizing the wavelengths. So I know that gamma is going to be short, but because why not? Radio is going to be long. Okay, so arrange in order from shortest to longest wavelength. I can therefore see it. If I start at D, I have X-rays, infrared here, microwaves here. So D is correct, right? Started as shortest, then I progressed until I reached the longest, right? So Xi, then M. So the correct answer will be D. 26. A wave is that frequency. What is the period of the wave? So period is actually 1 over frequency. So I have 1 over 5 times 10 to the power of 9. I'll put that down. That's 2 times 10 to the power of negative 12. That's 2 times 10 to the power of negative 10 seconds. And I'm trying to now look at these answers and say, which one is 2 times 10 to the power of negative 10? So if I have 200 picoseconds, that's 200 times 10 to the power of negative 12. So here I have 2 zeros. That's 2 times 10 to the power of negative 10 seconds. So the correct answer is going to be A. So we're just looking at that and saying, how can I be able to utilize the answer that I'm given to arrive at the correct answer that I want to arrive at? Okay. And then if I look at D, also is not correct because I have micro. That's going to be eaten or cancelled out by that. Then I have nano. Nano is going to go down because I have that 0. So it's going to go to negative 8. 3 statements about 2 progressive waves are listed below. Which statements must be correct for the 2 waves to be coherent? What is coherency? So coherency, I did some research, comes from the Latin word coherere, right? If you're interested about that, which means connected. So in Latin, coherence just means connected or stuck together. So it describes how 2 waves maintain a fixed relationship with each other. So it's sort of the predictability of how waves can interact. So it's important for waves to have coherence because I know what's going to happen in the future. If I have a wave moving like that and I have a wave moving like that, and I can predict what's going to happen next, what they're going to look like next, I can tell if they're going to meet. So that's why coherence is important. If they have a certain relationship, if 2 waves have a certain relationship, that's really good for me. So coherency basically is asserted by 2 things. Frequency, number 1. The frequency must be the same, right? You can't have a wave that's going like this, then you have another wave that's going like that. But they have different frequencies, dude. There's no way that they're going to be coherent, right? So frequency is a given. Amplitude really doesn't matter. right? We don't really care about amplitude. They can have different amplitudes because now constructive or destructive interference can now come into play, but they don't really have to have the same amplitude. Then the waves must be emitted with a constant phase difference. That is important because the phase itself has to be constant in order for them to have a fixed relationship that's present. So 1 in 3 will be correct, and the correct answer will be C. Question 28. Wave P and Q have the same amplitude. The waves meet in phase at point X and interfere to give a resultant wave with intensity I. The amplitude of wave P is doubled. What is the new intensity of the resultant wave at X in terms of I? Okay, there's a relationship between intensity and amplitude. So intensity is directly proportional to amplitude squared. So intensity would just be equal to K A squared. So for the first thing, two waves meet in phase at point X. So if you have one wave with an amplitude A, let's call that P. Another wave with an amplitude A, let's call that Q. If they meet, they form a resultant wave with an amplitude 2A. Let's call that R. And we're being told that that intensity is I. So I will basically be equal to K. My amplitude, remember, is 2A squared. So my I is basically 4KA squared. Right? So you're basically saying if I combine these two things, they're going to have double the amplitude. So I should expect the amplitude to be 2A. Substitute that into that equation, and I have the relationship for intensity and amplitude. Then now I've been told that the amplitude of wave P is doubled. So now you have a new scenario where P is coming with 2A, then Q is coming with A, and if they join together, they're going to give you 3A as the resultant. And your goal is just to find the intensity itself, right? So the new intensity will basically just be K, the amplitude itself being 3A squared. So I new would just be K A squared times 9. But hold on, KA squared, I over 4. Oh, that's interesting. So KA squared is I over 4, Oh, so I can put that here and say, IN is actually I over 4 times 9. Isn't that interesting? So 9 over 4, that's just going to wind up to 2.25. That's 2.3i. Right? So you're making these relationships. I is a squared, and I have to make sure that I'm talking of the resultant amplitude when I talk of the intensity for both of those instances. 29. Radio waves can be polarized. Radio waves are electromagnetic waves. They are transverse by nature. Sound waves cannot because they are longitudinal. So they can't be polarized. So radio waves are transverse. Sound waves are longitudinal. And that's important because you can't polarize longitudinal waves. Polarization is restriction of the motion of a wave in one direction. If you don't understand it, please watch my video. It really helps understand what polarization is and how it works. And once you've understood that, you should know that radio waves can be polarized, but sound waves cannot. Question 30. Light of wavelength lambda is incident normally on a diffraction grating with a total number n lines in width. If you don't know what a diffraction grating is, you're in luck. I'm showing it on the screen right now. That's what a diffraction grating is. So it consists of different lines with a certain width that's present. So my goal basically is to say, the moment you see diffraction grating, first of all, the moment you just see the word diffraction grating, I want you to do this. The moment you see the word diffraction grating in any question paper, just say d sine theta is equals to n lambda. Trust me, it's going to come in handy. This is the equation for all diffraction grating scenarios where d is the thickness of the line. So if you have n lines, n number of lines across a width of w, how thick is one line? Well, how thick is one line? Well, it will just be the width that you have divided by the number of lines that you have, right? Because you want to find how thick one line is, but you have a certain width and a certain number of lines. But w over n is what d actually is. So now, I can just go and say, w over n sine theta and n is the number of order, which is the second order maximum, 2 lambda. So n would just be equal to w sine theta divided by 2 lambda. The correct answer will be C. Question 31. Kirchhoff's second law is a consequence of a basic principle. What is this principle? We have two laws derived by, say, Kirchhoff. The first one is first law, conservation of charge. Second law is conservation of energy. So the correct answer is going to be B. Question 32. The diagram shows a circuit with a light-dependent resistor, an LDR. I love electricity. It's a very exciting topic once you get the hang of it, really. So the ammeter reads 0 current. That implies that no current flows through here. So whenever you see the word 0 current, it tells you that there is no potential difference across these 2 points. So let's say point P and let's say point Q. What it tells you is that there is no PD across these 2 points. Why? Because if there was a PD, if there was 2 volts here, there was 6 volts here, electrons would be like, let's go to 2 and help it go up. But if there's 6 volts, well, no one wants to move, right? You got 2 slices of bread, I got 2 slices, why should I share mine? Right? That doesn't make sense. So they won't move, right? So if the ammeter reads 0, it implies the current is equal in both instances. So I want to figure out, well, how much did this take? I started with the 12, right? You had your little electrons running. They arrived at this junction. How much did the 10 kilo ohms take? So basically you use this law, which says that if you want to find how much one resistor gets, it's that resistance over the sum of all the resistors up until n times the voltage that you have, the total voltage that you have. It's like sharing things, right? If you have 3 people, it's 1 over 3 times the things that you want to share. So the person on top, all the people times the things you want to share. So 10 on top, all the people, 10 plus 30 times the thing you want to share, 12. So basically the 10 kilo ohms gets 3. So if the 10 kilo ohms takes 3, that implies I'm left with what? Come on guys, you're left with what? 9. So I'll have 9 volts left here. So at this particular junction, I'm going to have 9 volts present. And then, because the ammeter reading reads 0, I'm also going to have 9 volts also present. I'm going to repeat again. I said, I want to understand how much did 10 kilo ohms take. And according to the resistor law, I started with the 12. So 10 over 10 plus 30 times 12 gives me 3. The 10 kilo ohm resistor took 3 joules of energy from the 12 joules that I started with. From the 12 volts that I started with, I needed 3 volts to overcome that resistance. How much am I left with? 9. So that I can overcome the 30. And that makes sense, right? 3 to overcome 10. So I need 3, 9 to overcome 30. So if there's 9 there, 9 there, my goal is now to say, so the 6 kilo ohms took 3 as well, right? So that I'm also left with 9 over there. And I want to find the resistance of the LDR. And I'm like, current V, R, how are they related? Well, V is equals to IR. So if I want to find the resistance across this, now I just need the current through that whole system. But it's important to know that if these took 3 volts and it's actually 6 kilo ohms, I can calculate the current because the current itself will just be V over R. So if it took 3, but the current itself is 6,000, that will be, but the resistance itself is 6,000, that will be the current. So if I now want to find the resistance of the LDR, it's just now going to be my voltage, or it took 9 divided by the current, 3 over 6,000, and that's going to give me 18,000. In other words, that's 18,000 kilo ohms. Right? Does that make sense? So you're connecting dots here. Right? And I would advise that you write this in your notes down. Whenever the ammeter reading reads 0, it implies that there's no potential difference. You're just trying to play with that fact to better understand how these questions can be solved. Question 33. We have a torch that uses 3 lamps connected in parallel and is powered by a cell of EMF 3 volts. So you have a cell, let's put it over here, with 3 volts. Then it powers your little torch, right? And your torch goes like this. And it's powered basically by all of this, like that. And you've been told that this is 3 volts, and this consists of 3 lamps connected together. So something like this. 1, 2, 3. Basically something like this. Okay. Each lamp dissipates 0.60 watts of power. And I know that they're in parallel. Whenever things are in parallel, they get the same amount of energy. Electrons just split. They decide to go their separate ways and abandon each other when they arrive at this junction. They go here, they go here. But they still have the same amount of energy. Imagine you're at the battery and you're getting bags of rice. When you arrive at a junction, do you lose your bags of rice? No, you just go your separate routes, right? One friend goes up, one goes there, one goes down, but they still have 3 volts. So I should anticipate that there will be 3 volts across all these different components. The potential difference will be 3. So if I look at this, I can be like, power is essentially V times I. So if I want to find the current across through one lamp, power is going to be 0.60 divided by V, which is 3. So I'm going to get 0.20 amps. But according to Kiko's law, it's split 3 ways. One up, one there, one down. So 3 ways. So roughly that current is going to multiply itself by 3 because it has to start somewhere before it splits. So I'll have 3 times 0.20. That's going to give me 0.60 amps. The correct answer will be C. I hope that makes sense. Question 34. A cell with internal resistance is connected to an LDR as shown, a fixed resistor and a voltmeter. The voltmeter reading increases. So I'm seeing this reading increasing and I want to understand why. The quantity that decreases should also be justified as the voltmeter reading is seen to increase. Let's think about this. The charge moving through the cell per unit time. So this is the current. Whenever I see an internal resistor, I think of the formula. EMF is shared amongst 2 things. The internal resistance with a small r, so big I, small r, plus, for these 2 guys, it's just big R and then R total for these small guys. This is the golden rule, guys. Whenever you're dealing with internal resistance, this is your go-to equation. So increasing the current, increasing I, increases R. So increasing I increases this value over here, right? Because you now have greater internal resistance. So that implies the amount of terminal voltage that you get out will be less because most of it is going in overcoming. It's going to go in the internal resistance because there's IR present. So increasing the current actually decreases the terminal voltage, hence decreasing the V that you get out of here because you have less of it since IR has increased, right? So some might say, but doesn't IRT also increase proportionally? Sure, but then if IR keeps on increasing and EMF stays constant, then at the end of the day, the IRT that you get will also start to get smaller and smaller and smaller and smaller because the IR keeps on increasing as well, right? So that is a problem because if IR keeps on increasing, the terminal voltage that you get out or the terminal PD itself also decreases, right? And then the energy transferred to the fixed resistor per unit charge, that's basically the terminal voltage again. I can't really say it decreases. I mean, if voltmeter reading is increasing, well, I should expect that the energy transferred to it also increases because the energy that it's getting has increased. So because the voltmeter reading has increased, right? So for the LDR that you'll be using, as the light intensity increases, the resistance drops. And as the intensity decreases, the resistance increases. So an increase in resistance implies that the voltmeter reading will actually decrease because the fixed resistor will actually get a lower voltage. But the terminal potential difference across the cell, if the terminal potential difference across the cell actually decreases, then if that happens, I expect that the current has increased, right? Remember, like I said, in order for the terminal potential difference to decrease, the current itself has increased so that the IR itself here increases so that this is the terminal PD. In order for the terminal PD to decrease, IR has to increase, right? So if current has increased, I know that for this one, V is equals to IR. but R is fixed. So if I increases, the voltmeter reading itself will go up, right? So the correct answer will be D. Does that make sense? If the terminal PD itself goes down, IR goes up. It has gone up to keep EMF constant, so I is increased. But V goes to IR. If I increases, the V reading will increase and increase and increase and increase. But the other ones don't work for the reasons that I've stated above. Question 35. The circuit contains a cell with negligible internal resistance. Then we replace that with an EMF source that has significant internal resistance. So we have this scenario where we now have a system with, significant internal resistance, something like that. So the effect on E, the EMF doesn't change, right? What you get out is what you get out. It's now just being shared amongst two things, right? That's how internal resistance works. You have these little soldiers hanging on to, the big thing, that they just take it and take it and take it. So E really doesn't change. No change in E. But V, the V that you get across here is what's decreasing because the internal resistance is going to take some things. So the V that you're going to get across here is the one that would then decrease as a result. So the correct answer is going to be C. Question 36. In the circuits shown, the batteries are identical and all have negligible internal resistance. All of the resistors have the same resistance. The diodes have zero resistance when conducting and infinite resistance when not conducting, so nothing passes through. In which circuit is the current in the battery the greatest? So let's compare and think. We have E here, EMF, E here, EMF, E here, EMF, E here, EMF, and E is equal to IR. So in order for the current to be the greatest, current will be equal to E over R. The smallest the value of R, the smaller this value is, the bigger this value is. So we just need to look for a setup with the smallest resistance. That's it. So if this is R and this is R, my color moves like that. Whoa. Allows it. I arrive here. So R plus R, my total resistance will be 2R. If I go here, R allows it. I'm blocked. So the only resistance present is R. If I go here, allows it. If I go here, I'm blocked. So the only resistance here is R. If I go here, allows it. If I go here, allows it. So in total, 1 over R plus 1 over R, that's in parallel, to the power of -1 is basically R over 2. So I get the smallest resistance in A. Hence, I get the largest current in A as well. Does that make sense? So you're just looking for a system with the largest value, with the smallest value of R to give you the largest value of I that is actually possible. Question 37. Potentiometer. I love potentiometers. They're pretty fun. A little bit challenging, but they're doable. So a potentiometer, basically, at different lengths, you experience different resistances. Remember, resistance is basically proportional to length, right? You've done this in IGSE or O level, and resistance is inversely proportional to area. So the bigger the length, the bigger the resistance. The bigger the area, the smaller the resistance, and vice versa. So you had a whole wire here of length 0.96, and the resistance was 0.50. So you want to figure out what's the potential difference even to begin with across this wire. So if it's 0.5 and 0.5, these guys share, right? Even split. You get 0.75, I get 0.75, and we're both happy. Cool. And then now, okay, this length is 0.64, but then that's when the galvanometer reads 0, implying that the current or the EMF across these particular positions is the same because the galvanometer reading is actually 0, right? So you're looking here, you're saying I have 0.64 meters, then the total length here is 0.96, but then I have 0.75 to share. How much did 0.64 get? Same as R1 over R1 plus R2. So like how much does 0.64 get out of 0.96 if you're sharing 0.75? And if you punch that in your calculator, you're going to get 0.50 volts and 0.50 volts will also be the value of E, so that the galvanometer doesn't read anything. So 0.50 will also be the value of E. Fundamental particles, particle physics, amazing topic, right? Which particle is not a fundamental particle? That's a neutron. An electron neutrino, that is a fundamental particle. Fundamental is you can't break it down into anything simpler. Charm quark, fundamental. Quarks are fundamental particles, but neutrons are not, because they're made up of quarks as well, right? Question 39. Fluorine isotope 89 undergoes beta plus decay. So basically in beta plus decay, you have a proton that gets converted to a neutron plus 0,1 B plus 0,0 VE. You're wondering, how do I cram this equation all at once? Well, you don't have to. Remember, it's beta positive, so you can be like P, proton. So start with a proton, turn it into a neutron, then try to make the numbers balance. If it's beta negative, N, start with a neutron, put a proton, then make the number balance. Just remember now to put an anti-neutrino for this, and then put a neutrino for the other one. Okay, so how many neutrons are there in a nucleus of the stable isotope that will be present? Okay, so if I start with 18, 9, and F, if I lose one proton, I'm left with 8 protons. Then I gain one neutron. I now have 18 plus 1. So now I have 19. So 8 minus, 18 as a whole, right? Because 18 is neutrons plus protons, right? So the neutron number drops by 8, and then that 18 just goes up, right? So because I've lost a proton and a neutron, 18 just remains the same, but the meaning itself has changed. Okay, so now I'm like, I have 18, I have 8. 18 minus 8 is going to give me 10. So the neutrons are going to be 10, right? Question 40, the last and very least. The last and definitely not the least, that is. Which statement is correct? A baryon is a hadron, that is correct, but it consists of 3 quarks, not 2. A meson consists of 2 quarks, not 3. An electron is a fundamental particle and is a lepton. Yes, that's correct, because an electron is not affected by the strong nuclear force. It's found outside of the nucleus. So it is fundamental, and it is a lepton because it's found outside of the nucleus. I hope that makes sense. So that about wraps it up. I hope this made sense. I hope you're able to understand bits and pieces of it. If anything is unclear, please do put it in the comment section below, and I'll be happy to address it. And if you've made it this far, it means you genuinely like the content. So please do subscribe so the channel grows and we can be able to help many people. Thank you guys for watching, and I'll see you in the next one.